Today I'm going to go through some GCSE slides for Edexcel IGCSE Units 4 and 5, which is energy and part of solids, liquids and gases. It will not be able to do the whole of the 2 units, so this will be the first video and I'll do some others in the build up to the mocks. Okay, so energy and solids, liquids and gases go very well together, and really it's very easy to revise them at the same time. So energy is all forms of energy, and then in solids, liquids and gases it refers to particle properties and the thermal energy that they contain in terms of movement of their particles, which includes therefore the changes of state that occur between solids, liquids and gases. Okay, so we're going to start off with energy transfers. So recently, in the last few years, they've changed what used to be called energy types, and it used to include any type of energy that existed, and they now describe them as energy stores. So if you can actually think of a source of energy that can store like in chemical terms or kinetic terms. So for example, here's the list. There are 8 energy stores, and then there are 4 types of energy transfer. So differentiating between stores of energy and transfers of energy. So I'm going to explain that using the following slides. So it's important that when you get questions in the exam relating to 4.2 in the syllabus for Edexcel, you need to distinguish between the transfer from one store to another. Now here are 8 energy stores. So the 8 energy stores are chemical, kinetic, gravitational, elastic, thermal, magnetic, electrostatic and nuclear. Whereas in the old system you could always also have light, heat, and sound, for example. So they're no longer considered energy stores because you can't store light, you can't store sound, and what was the other one I gave you? You can't store electricity. Okay, so electrostatic, you can store electrostatic energy. So it could be, for example, if the Van der Graaf generator, it has a store of static electricity. When you charge something up, there is a store there, it's an energy source. Or when 2 charges are separated, they have a potential energy between them. A bit like if you lift a mass in a gravitational field, that has a form of gravitational potential energy. So if you let go of it, it will move towards the source of that energy, which will be gravitational. And same can be said if you separate 2 charges. And if you're doing advanced level physics, you will know that gravitational potential energy and electrostatic potential energy are very similar mathematically. Okay, so we need to distinguish between energy stores and the 4 energy transfer mechanisms. So for example, I've put mechanical energy transfer next to kinetic and gravitational. So whenever there is work being done, physical work being done, so you are lifting something, for example, from the floor onto a shelf, you're doing physical work, and in the process you are increasing the gravitational store of that object. So say you lift a bag or a suitcase, or on an aeroplane you lift your carry-on luggage into the what do they call the bits above the seats where you can store them. But that the weight that you lift multiplied by distance is kind of, you've given that bag gravitational potential energy. So that's why they always make sure those what are they called anyway? Those cupboards that are above the seats in an aeroplane are closed securely. So if there is any turbulence that they're going through, the bags don't fall on people's heads because they would then store gravitational potential energy. But the work done to put the bag in there is a mechanical energy transfer. So whenever there's any physical work done, there is called a mechanical energy transfer. Okay. Now it could be that the bag then does fall on your head, and that there is some work done. But this time you're not doing the work. It's the gravitational field that's doing the work, and it supplies the force, and it will lose height. And in losing height, that's the distance. So in this case, the gravity is doing the mechanical energy transfer. Okay? So you need to distinguish between what is an energy transfer and what is a change in store. So for example, if the bag falls out of the compartment above the seats on a plane, then it will convert from gravitational potential energy. It will lose some of its gravitational potential energy that you gave it by putting it in there in the first place, and it will convert it into kinetic energy before it hits the floor, or hopefully doesn't hit the person sitting on the seat underneath it. Okay, so mechanical energy transfer can be work done either by the gravitational field, or it can be work done by a machine, or it can be a work done by a person lifting something. Then I've put the difference between thermal as an energy store. So internally there is thermal energy stored in everything. Everything that has some a temperature has a degree of internal energy in it, and it's due to the vibration of the particles or the movement of the particles. So when it's stored inside a material, we say it contains thermal energy as a store. But when heat transfers from, say, a hot material to a cold material, that energy transfer is then called heating. Yeah, so it could happen in solids by conduction. It can happen in the atmosphere through air currents, hot air rising, for example, and that's called convection. And it can happen between a hot object that's glowing. It will radiate heat, and that radiation will be in the form of infrared waves. Okay, so waves are a form of radiation transfer or heat transfer. And then you'll see at the bottom I put radiation example, light or sound. That's another form of transfer of energy from one place to another. So for example, the sun gives us light and it gives us heat. It also gives us other forms of electromagnetic energy by radiating them through space. So there is a connection between heat transfer, when we're talking about raising the temperature of something, and electromagnetic radiation, which you studied in the waves topic. So it's become quite technical to be able to distinguish between these forms of energy. So then electrostatic is a store of energy. I've put electrical energy transfer next to it. And if you want to do some electrical work, for example, rather than having a store of electrostatic energy, if you can release that electrostatic energy through a current, for example, you know that an electrostatic Van de Graaff generator, for example, can store quite a lot of voltage. If it can then give out a current, if you can make that form of static electricity move, then you've got an electrical energy transfer, and it could result in a spark, and the spark would be the electrical transfer of energy. Okay, you could say that electrical work is being done rather than mechanical work being done. So I hope this clarifies the change in the way physics is looking at this, especially in GCSE. They do want you to be aware of the 8 energy stores and the 4 energy transfer mechanisms which are listed in this table. And I hope you found that useful as an introduction to this video. Okay, now the ultimate energy source on Earth is obviously the sun, because we've already talked about the sun radiates heat and light and other forms of radiation through the vacuum of space, and it will come, and for example it's the cause of photosynthesis. So if the beef that you're eating beef from a cow, the cow ate the grass, and the grass got its energy from the sun through photosynthesis. Okay, so ultimately, most energy sources on Earth originate in the sun. Okay, so that's just some background information. So energy transfers, to describe an energy transfer, for example, for a battery operated torch, we need to consider 3 steps. Okay, you need to consider what is the initial energy store. Well, that will come from the battery, and it will be a chemical store. So a battery contains chemical energy, and it's been engineered by chemical engineers. Okay, and then that converts into a thermal store, which is in the torch. The torch gets hot, and it gets so hot that it glows. And you've got to draw the arrow showing the energy transfer, and the energy transfer in this case in a torch will be electrical. There'll be an electrical energy transfer which takes the energy from the battery and gives it to the bulb, and it ends up as a thermal store. So basically the filament lamp here, it gets hot, and it gets so hot that it starts to glow, and we call that white hot, or in this case it would be more like yellow heat. And that's what happens to our sun. Our sun is glowing and has a thermal store of energy which allows it to do that. So what are the energy transfers for the following? An electrical immersion heater, that's just a heater that gets its energy input, so it's transferring electrical energy, and it will give out thermal energy. Okay, so it will convert the by electrical mechanism of the mains electricity, so wherever that comes from, and of course ultimately that will be burning a fuel. So again, it will be a chemical store which is converted electrically by the immersion heater to give you increase in a thermal energy store. Say you want to heat up ice and convert it into water, so you could do that. Or you would an electrical immersion heater is a heater in a kettle if you want to boil water. Okay, so, and then a rock falling down a hill would be the second example. It's converting gravitational potential energy by means of a mechanical energy transfer, and basically the gravitational field of the Earth is doing the work, and it's converting it from gravitational potential energy high up on the top of the hill to at the bottom of the hill. It will convert it into kinetic energy. The store will go from gravitational to kinetic. An arrow about to be fired through using a bow and arrow, then you've got an an elastic potential energy in the bow is then going to convert it into a kinetic energy, and the transfer mechanism is by means of work done physically. You're stretching it, so it's a mechanical energy transfer that causes that to change the energy store from elastic into kinetic. Okay, so that's an introduction to the terminology required for the exam. And of course, you have the principle of conservation of energy. That means energy is never created or destroyed. It just changes from one form to another. Okay, so you need to be aware of that. But there will be some what we call waste energy, and that's kind of unwanted source of energy. So in a light bulb, for example, we get heat, especially with the filament light bulbs, the old-fashioned ones, which are still in the GCSE for electricity because they want you to know how they resist electricity. In this example, heat is wasted and is transferred to the surroundings, and it becomes very difficult to use, and that's why we call it wasted heat, because it's not in a useful form. And then you can, for example, describe the following energy transfers and state the wasted energy or energies. For example, a vacuum cleaner is doing some mechanical work by picking up bits of dust. So that's what it's designed to do, to clean your carpets, for example. But in the process, it's making a lot of sound and transferring sound to the environment, which ultimately is just vibration of molecules. Sound is just vibration. Noise, if you like, is unwanted sound. And eventually it will just become background movement of particles. So in a way, it's a form of heat to the surroundings. A TV also, you want the light radiated from the screen so you can see the pictures, and you want the sound so you can listen to the audio. So these are forms of energy transfer which are wanted, but in the process, again, some of it is wasted in the form of unwanted thermal energy. Okay, so it will go to the surroundings. And then anything electrical, like a dynamo or a generator, will also, due to the resistance in the wires and friction in the moving parts, will waste some energy. Even though the electrical energy transfer will do some useful work, it will also transfer some of the wasted energy as thermally to the surroundings. Okay, so you need to be aware of this when you're answering exam questions. And efficiency then is how much of the transfer goes into the wanted or the useful energy output. Yeah, for example, a TV uses 200 joules electrically, and it gives off light, it gives off sound, so these are forms of radiation, and some of it will transfer into heat. So the useful output would be 80 plus 40, 120 divided by 200. If you want to work it out as a percentage, you multiply by 100, and that'd be 120 out of 200, so that's 60%. So that's how you work out the efficiency. Okay, obviously you don't want the heat, it's going to go into the surroundings. So energy transfer diagrams, let's say a bulb transfers 100 watts electrically, that's 100 joules per second, 20 joules per second into light output, yeah, so light radiated in the TV or the bulb, and you want that, and the rest of the heat transferred to the surroundings thermally. This can be represented by a Sankey diagram. And in a Sankey diagram, the width of the arrow represents the amount of energy in that form or in that aspect of the transfer. So here you see that the green arrow is the wasted form. It's unwanted 80 joules per second turns into heat from the electrical work that's being done. And only 20 joules per second is radiated as light in this particular example. So that means it's only 20% efficient. So Sankey diagrams are a visualization of efficiency. Okay, the blue arrow is useful, the output energy you want, and the green arrow in this case is the wasted energy. So you can change efficiency situations into what they call Sankey diagrams. And you could be asked to draw one of these, and you've got to draw the width of the arrow to scale. Okay, so Sankey diagrams in general, for example, a kettle, which is using 2000 watts, will be 2000 joules per second. Some of it will be wasted heat. Some of it will produce sound. Obviously, you don't want sound, but you actually, in this case, you want all the heat to be transferred to the water. Now, when I did this with my GCSE Year 11 students, we saw that only 50% of the heat that came electrically, the electrical work done by the kettle, only 50% of it went to the water when we were trying to boil the kettle of water, because we could work it out using specific heat capacity calculations, which comes up later in Unit 5. So if you work out the energy value for each part of the arrow, you just do the thickness, so if it's drawn to scale, you can work it out. So you can work out, for example, that 5/10 of it is green, 2/10 of it, each square representing a percentage, and so on. And 3/10 of it becomes sound. So you could work out the efficiency. In this case, it'll be 50% efficient because of the 10 pink squares, 5 of them turn heat into the water, and that's what we wanted to do. 20% goes into wasted heat, and 30% goes into unwanted sound energy, which is an unwanted result of boiling a kettle of water. Then a computer, for example, again, is using 150 joules of electrical energy input, so it's electrical work that's being done inside the circuitry. 20 joules per second is wasted, and 10 joules as heat to the surroundings. So computers get hot and they transfer thermally to the surroundings by conduction or radiation, yeah, or heating the air inside, and that can be transferred by a convection current. So these are all mechanisms of heat transfer, and therefore you could work out that the useful light and sound from the computer would be the green arrow, which you've got to work out is 70%, because it's 20, 30, it's out of 150 joules, so they haven't made it easy for us, so you'd have to work it out. Out of 150 joules, 30 joules is wasted, that's a fifth, so 20% is wasted. That means 80% is left for useful light and sound, because the computer needs to sometimes give you sound output, okay? So again, you've got to be able to work out the efficiency using the equations that I gave you before. So going back to the equation, useful output, what you want it to do, divided by your energy input. And often the energy input with machines is electrical. Yeah, so you've got to work it out by the power of the device. I can see that red arrow, the E has slipped off the page. So that's electrical energy used, okay? Okay, so we've gone through the Sankey diagrams there. For the width of the arrow shows the amount of the energy going into each energy transfer. And here's some examples I gave you. And these are some questions you could try. And if you want to stop the video and do these using the equation that I gave you on a previous slide, see if you can change the subject to the formula for question 3. And the answers are on a slide that's coming up. So if you want to stop the video and use this equation, yeah, so the equation at the bottom here, to be able to solve those questions, you can go back to the slide before, yeah, see if you can work them out, and then when you've done it, you can start playing the video again, and I'll stop the video after the answers to those questions. Okay, so in 3, 2, 1, I'm going to transfer to the slide with the answers, and you'll be able to check if you got them right or not. So this is a self-assessment task for you. Okay, so in 3, 2, 1, here are the answers. Okay, that's how I've calculated them. So you'll be able to work your way through. I've used the equation useful output over input energy, put the values in. I haven't worked it out as a percentage because they haven't asked me to, but the percentage is given in brackets. So hopefully, if your math skills are good enough, you will be able to do that. The second question, the E has gone on the previous line, so you just need to, E is the efficiency. Again, useful output divided by the energy input, in this case is 60% efficient due to the ratio of the useful output over the input. The final question, it gives you the efficiency and it tells you how much energy the steam engine delivers. Yeah, so that's the output. They want you to work out the input energy, which was chemical, because obviously a steam engine will burn coal or something to be the source of its input energy. So to change the equation round, input energy will be useful output over efficiency. And if you can't change the subject of the equation round, you'll need to go and do some revision on that. I'm not going to go through the maths of that. And if you do that, the answer is 40,000 joules. So I hope you found this introduction to energy and efficiency useful. Yeah. The next thing we're going to go on is to look at electrical energy and power, which I'm not going to do today, but I'll just show you that electrical energy, again, is covered already. It's a kind of energy transfer. So instead of doing physical work, you're doing electrical work, and this allows you to do the calculations. Remember, 1 watt is always 1 joule per second, and here is the equation that you've got to use. And I will let you have a look at some questions, and I'm going to stop the video without doing the answers, and I'll start the next video on this with this equation, yeah, and give you the answers to the following slides. So you can try and do these on your own, and I'll come back to you later. So I'm going to upload this video into YouTube. If you found it useful, please like, share, and subscribe, and I'll do more videos in the build-up to the mock exams. Okay, thanks for watching. Bye for now.